Hello everyone, this is Professor Roman. Welcome to the 23rd video in my video lecture series, An Introduction to Discrete Mathematics. In this video, we're going to explore some of the properties of binomial coefficients. We've already looked at this simple relationship, n choose k equals n choose n minus k. And I mentioned that aside from proving this algebraically, there is a combinatorial proof, namely choosing what you want, taking it out of, let's say, the box containing everything, is equivalent bijectively to taking out what you don't want and tossing it away. Just to be a little more formal on that argument, suppose S is a set of size n. Then we can associate to each k combination A taken from S its complement in S. And that's an n minus k combination. And since the map that sends A to A complement is a bijection, something you would want to prove specifically, but it's just a couple of sentences. It's a bijection from the set of all k combinations to the set of all n minus k combinations. The two sets have the same size, which is exactly what this says. Another one of the simplest and most useful properties of binomial coefficients is this relationship here. N choose k is equal to n minus 1 choose k plus n minus 1 choose k minus 1. And this holds for any n bigger than or equal to 1 and k bigger than or equal to 0. This formula is known as Pascal's formula. And as to its proof, we would first want to dispose of some degenerate cases. If k is 0, then this formula reduces to 1 equals 1 plus 0. And that, of course, is true. If k is bigger than n, this is 0, this is 0, and so is this. So we get 0 equals 0 plus 0. So that's true. These are not very useful, but at least we don't have to make further restrictions on n and k. It might be easier to remember. But since we have taken care of the degenerate cases, we can now assume that k lies between 1 and n. Identities involving binomial coefficients, like this one, can often be proved in two entirely different ways, as we've seen with the simple formula. Where is it? This one here. You can prove this algebraically by writing it in terms of factorials, or we can use a combinatorial proof. And that's the case for most combinatorial identities. The purely algebraic version looks like this. And it's not very pleasant, but also not terribly difficult, just a matter of arithmetic, basically, writing the two binomial coefficients in terms of their factorials, noticing that the numerator is the same, so we factor it out. We still have the sum of these expressions. And we can, if you look here, we would like the denominators to be the same. And so we can raise this to n minus k by putting an n minus k in the numerator. Now we have the same denominator here as we have here, but we have to put a k up here to raise this k minus 1 factorial to k factorial. And now we can factor out the common denominator and simplify. Okay, so it's pretty routine. Combinatorial proof is much more interesting. So consider, the first thing you generally do with a combinatorial proof is you set the underlying set, and the most convenient set of size n for this purpose is the set 1 through n. Now the left-hand side just counts the number of subsets of size k taken from this set S. Okay. To see that the right-hand side also counts this number, notice that the right-hand side involves choosing from a set of size n minus 1. It's what's common to these two terms. So in some sense, one of the elements of the underlying set S has either been chosen already or it's been ruled out. And we're free to take that integer to be any one we want, but 1 is convenient, n is convenient, so we'll take n. And because there are two terms, this is begging us to divide the problem into two parts. What are the obvious choices? The k subsets of S that contain n, and the k subsets of S that do not contain n. The k subsets of S that do not contain n are simply the k subsets of this set, 1 through n minus 1. And there are n minus 1 choose k of those. And that, it makes us happy because that's the first term here. The k subsets of S that contain n correspond bijectively to the subsets of this smaller set of size k minus 1, because we have to toss in n. And there are n minus 1 choose k minus 1 of those. That's the second term. These two groups, contain n, don't contain n, are obviously disjoint, so the total number of k subsets of S is their sum of the numbers of each type. And that's Pascal's formula. So this may have gone a little too quickly, but I would urge you to go over it yourself until you can reproduce this argument, because this is one of the simplest types of combinatorial proofs. They get more involved, and we'll see another one in a minute. But this is, you can always resort to the algebraic proof, although sometimes that gets really messy. But the combinatorial proofs are much more satisfying and give you much more information. Pascal's formula is named after the French mathematician Blaise Pascal. So is the Pascal programming language. Pascal was one of the founders of probability theory, along with Pierre de Fermat. Although Pascal's formula was actually known to the Chinese sometime around 1100 AD, so it's quite old. Here's another interesting formula. It says that for k between 0 and n plus 1 choose k plus 1 is the sum of I choose k as I ranges from k to n. Now, it wouldn't hurt if you were up to it to try to see if you can find your own combinatorial proof of this. Frankly, the algebraic proof looks like it might be quite difficult. So let's go to the combinatorial proof. Let S be the set of integers from 1 to n plus 1. Now the key here is similar to the one in the previous proof. On the left side, in this case, there is something common to every term, and that is the k in the lower, the lower number. and the upper number ranges from k to n. So again, since the right side involves a choice of k plus 1 integers, but the left side only involves choices, plural, of k integers, an integer has already been chosen or ruled out or something. This leads us to the idea, we in the previous proof, we did partition the problem into two parts. Contain n, does not contain n. Similarly, here we have led to the idea of partitioning the total choices, n plus 1 choose k plus 1 choices, of k plus 1 elements into blocks, but now we need something a little more sophisticated. And in this case, we'll divide the elements into blocks based on the value of the largest element chosen. We could work with a different element, but generally speaking, when you have a set, you're trying to break things down. You look for extreme elements, the smallest or the largest. Okay. So suppose that the largest element chosen is I. The remaining k elements, because we're choosing a total of k plus 1, has to come from the set 1 through I minus 1, because I is the largest one we've chosen. So there are I minus 1 choose k choices for these k elements. Now, if you look back up here and you look again at I minus 1 choose k, you might get depressed. Not to worry, we're not done analyzing the problem. Our hope is that we're going to be able to bump this up by 1. Also, I has to be between k plus 1 and n plus 1. The largest element in this setup here, of course, can't be bigger than n plus 1, but I has to be bigger than or equal to k plus 1 because we're choosing a total of k plus 1 elements. So we can count the number of subsets of size k plus 1 by summing these binomial coefficients over this range. And here is that sum. Binomial coefficient I minus 1 choose k, I goes from k plus 1 to n plus 1. Now, you remember something we did a long time ago. I think I called it index shifting or something. If we want to bump I up by 1 to get I in the upper number, we have to reduce the range of I, the range of summation of I. So we drop it down to I goes from k to n, I choose k. That's exactly what's written here. Okay. Another very nice example of a combinatorial proof. And in this case, it's going to be far simpler, I think, than an algebraic proof. I've never attempted an algebraic proof, but dealing with this sum looks kind of ugly. Here is, for the record, the binomial theorem, which supplies the name for the binomial coefficients. I have a feeling you know this quite well, so I'm not going to dwell on it. If you have, say, real numbers x and y, and n is a non-negative integer, x plus y to the n is this sum called the binomial formula. And here is a proof of a somewhat combinatorial nature, which I would suggest you think about yourself. Examples, I don't think I need to dwell on this. You can read it for yourself. Here is, however, an interesting application of the binomial formula. if we set x equal 1 and y equal -1 in this formula, we get 0 to the n here, and what comes out looks like this. N choose 0 minus n choose 1 plus n choose 2. The signs alternate till you get all the way up to n choose n. That's equal to 0. Each term where k at the bottom number, n choose k, where k is even, is going to occur with a positive sign. N choose 0, n choose 2, and so on. The odd numbers at the bottom will occur with a negative sign. Moving the odd terms to the other side, when k is odd, we get this. Sum n choose k, k goes from 0 to n, k even only, equals the same sum, k is odd. So in words, this tells us that the number of odd-sized subsets of any set is equal to the number of even-sized subsets. And that's kind of neat, actually. There are several more examples of formulas involving binomial coefficients in the exercises, so if you find these to be interesting puzzles to solve, you can look there. I'm going to conclude with a discussion of Pascal's triangle. That's shown here, the first part of it, in this figure. And I have bold-faced the entries in each row that are largest. So 2 is the largest entry in this row, a couple of 3s, largest entry in this row, and so on. The nth row of Pascal's triangle, n could be 0, so we'll start this at row 0 at the top, contains these n plus 1 binomial coefficients. So the first row contains 2 binomial coefficients. When n is 1, n plus 1 is 2. These are the binomial coefficients in the expansion of x plus y to the n. Here is a general piece of Pascal's triangle. Okay. This row, in general, would have a lot more stuff in it, but I just want to focus on a little portion of the triangle. Pascal's formula can be seen here, and I've drawn a couple of arrows and a plus sign in red. This is Pascal's formula. It says that if you want to add two adjacent binomial coefficients in the same row, you will get the same as the binomial coefficient in the next row down that sits in between these two. So maybe that'll help remember the formula. I don't know. Now, if you look at the first few rows here in this triangle, what you will notice is that the coefficient, let's go back again, scan this third row here, or second row. The binomial coefficients increase till they hit the middle, then they decrease. Look at this row. Again, 1, 4, 6, and then they drop off. In fact, there's a symmetry here, and that's because of the formula we had. Choosing what you want is equivalent to choosing what you don't want. So the binomial coefficients climb, then they descend. In the remaining rows, like the fourth row here, I'm sorry, I did it again, the third row, there's a duplicate value. Okay. So every other row has a single maximum value, and the other rows have a duplicated maximum value. But all these maximum values occur in the center of each row. And by center, of course, in some cases there's a single center. In other cases there are two centers in a sense. Okay? But of course all this is just a discussion based on the first few rows of the triangle. So what we need to do is formulate a conjecture here and then prove it. Well, the conjecture looks like this, that when, let's start here. Okay. In each row, the binomial coefficients increase as k increases until k reaches the middle of the range from 0 to n. Then they begin to decrease. Specifically, if n is even, then there's an odd number, n plus 1, of binomial coefficients, so there is an exact center. It's n, choose n over 2. Okay. That's should be the maximum value, we conjecture. When n is odd, we're going to have a double maximum value. N choose n minus 1 over 2, n choose n plus 1 over 2. These are always equal. We know that because of the choose what you don't, choose what you want, choose what you don't want. Okay. The sum of these two and bottom numbers is equal to n. So we can say in loose terms that there are more subsets of a set of size n that have middle size, which is roughly n over 2. It might be n over 2 exactly, or it might be, if n is odd, then it's going to have to be on either side of n over 2. So for example, a set of size 10, there are more subsets of size 5 than any other size. For a set of size 11, there are more subsets of size 5 or of size 6. And be careful what I'm saying here. More subsets of size 5 and more subsets of size 6 than any other sizes of subsets. Okay. So let's put this in a theorem and prove it. Let n be a positive integer if n is even. The largest value of n choose k, and k is going to range from 0 to n, occurs exactly once at n choose n over 2. If n is odd, the largest value of n choose k occurs exactly twice at n choose n minus 1 over 2. That's the integer just less than n over 2. It's the greatest integer in n over 2, also equal to n choose n plus 1 over 2. And so it follows that all the binomial coefficients n choose k are less than or equal to n choose greatest integer in n over 2. So how to prove this? Well, one way, anyway, is to look at the ratio of two consecutive binomial coefficients. R sub k is n choose k divided by n choose k minus 1. And the usual arithmetic with factorials reduces this to n minus k plus 1 over k. Therefore, n choose k minus 1 is less than n choose k. The denominator is less than the numerator if and only if the ratio is greater than 1. And since this is the ratio, we can solve for k. So this is if and only if k is strictly less than n over 2 plus 1/2. And the other two rows are found the same way. Okay, these two are equal if and only if the ratio is 1, if and only if this equality holds. Now, if n is odd, n over 2 plus 1/2 is an integer. And so these expressions here, which occur 3 times, they're actual integers. And so we can find the maximum value of the binomial coefficients right here. Okay. If k is less than this value on the right here, we're still climbing. If k is greater, we're descending. We hit the maximum right here. And that's this binomial coefficient, which we know to be equal to this one, and that's simply this equation here. If n is even, n over 2 is an integer, and this middle equation, or biconditionals, cannot happen. K has to be an integer, n over 2 plus 1/2 is not an integer, so that's ruled out. And k less than n over 2 plus 1/2, because k is an integer and n over 2 is an integer, it means k is less than or equal to n over 2. K bigger than this is equivalent to k bigger than n over 2. If this is kind of vague in your mind, try some numerical examples. N is even, choose n equal to 10, okay, and see how it works out. So these two statements here tell us that there's a single maximum value at k equals n over 2. Because we're climbing as long as k is less than or equal to n over 2, but as soon as we go a step bigger than n over 2, we start to decline. So this is not a very pleasant proof. I don't know one that is pleasant, really, but it is a proof. And I'll leave this for you to do. Well, that concludes this section, but since the next section is quite small, I thought we would do that in this video. And this section is entitled Poker. So what I want to do is apply what we have been discussing about counting techniques to something really valuable, and that is the counting of poker hands. If you don't know how to play poker, it's not a problem. You can still follow the discussion. But if you're not interested, you can skip the rest of this video and it won't prejudice the remainder of the course. I am going to assume you're familiar with an ordinary deck of playing cards. There are 52 cards in the deck. Each card is one of 4 suits: spades, hearts, diamonds, or clubs. Each card is one of 13 denominations or kinds or ranks. 2, sometimes called deuce, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, ace. This is in order of increasing rank. Now, a poker hand consists of 5 cards. So we now know that there are 52 choose 5, or 2,598,960 possible poker hands. Okay. For example, 2 types of poker hands are the flush, which consists of 5 cards in the same suit, any 5 cards in the same suit. So this would be called a spade flush. And a straight, which consists of any 5 cards in consecutive denominations. So ace, king, queen, jack, 10, or you can read it the other way, 10, jack, queen, king, ace, 7, 6, 5, 4, 3, ace, 2, 3, 4, 5. So you'll notice here that an ace has the unique property that it can either be the high card in a straight or the low card in a straight. It's the only card with that property. Actually, the number of poker hands of a given type is less useful to a poker player than the probability of getting that particular type of hand. And so to compute probabilities for a particular type of poker hand, all we have to do is divide the number of hands of that type by the total number of 5-card hands, which we've already seen. And I'll do that at the very end of this discussion of poker. From our point of view, it's the counting of the number of hands that's more important. So let's go through the poker hands in descending order, the types of poker hands, and count how many there are. Royal flush is the best possible hand. It is the ace, king, queen, jack, 10 of the same suit. Well, there are only 4 royal flushes out of the entire 2 million, let's call this 2,600,000 roughly. So they're extremely rare. I've been playing poker since I was 15 years old, and so that's 61 years. And I can't remember if I've ever had a royal flush. I may have had 1 or 2 in that span of time. Straight flush. This is 5 cards that form both a straight, so they're consecutive denominations, and a flush, same suit. A royal flush fits that property, but so do hands like this. 7, 6, 5, 4, 3 of hearts. Ace, 2, 3, 4, 5 of diamonds. Those are straight flushes. This would be announced to the other players as a royal flush. This would be announced as a 7 high straight flush, 5 high diamond straight flush, or just 5 high straight flush. So a royal flush is a straight flush, but you call it a royal flush because that's a higher type of hand. Okay. In poker, if 2 players have straight flushes, the hand that contains the higher denomination cards is higher ranking. So a 7 high straight flush is higher ranking than a 5 high straight flush. The suits don't matter, so in poker, the suits do not have a ranking. Okay. How many straight flushes are there? Well, in this case and in all the following cases, the way to think of it is, how do you construct such a hand? Imagine you're sitting at a table with a deck of cards in front of you, and somebody says, make me a straight flush. I want to see what it looks like. What do you do? Well, first you choose a suit. Spades, hearts, diamonds, or clubs. Then you choose the smallest card to form your straight flush. If that's a 7, then you know you need an 8, 9, 10 jack of that same suit. In other words, the suit and the smallest card have uniquely determined a single straight flush. Now, there are other ways you could do this. Those are 2 tasks. Those are the ones I chose. You could do the tasks in reverse order, or you could choose a suit followed by the largest card for that particular straight flush. But we'll stick with the smallest card. What are the possibilities for the smallest card? Ace through 10. So there are four suits. You choose one. There are 10 smallest denominations. You choose one. That's 40. 40 straight flushes. And that includes the 4 royal flushes. So 36 straight flushes that are not royal flushes. 4 of a kind, that means 4 cards of the same denomination. Every poker hand has 5 cards, so there'll be a 5th card. And that 5th card is irrelevant. So, for example, 4 jacks and toss in the 5 of diamonds. So you would just call this 4 jacks. 2 4 of the kind hands are ranked according to the denomination of the 4 matching cards. So 4 jacks is higher than 4 tens. How do you form a 4 of a kind hand? Among the 13 denominations, choose one. There are 48. So once you've done that, you have fixed the 4 of a kind. If I choose jacks, I have 4 jacks. I still need one more card. There are 48 other cards. Choose one of those. Here it's the 5 of diamonds, and you get your 4 of a kind. There are 624 such hands. Next in order of rank, lower rank, is full house. 3 cards of one denomination and 2 cards of another. This would be announced as a full house 9s over jacks. You say the 3 of a kind denomination first, or you could say 9 over jacks full house. Colloquially, you will hear people say 9s full of jacks. Some people call these full boats. I don't know where that term came from. I never use it. Okay. The rankings among the full houses is by the denomination of the 3 of a kind. And that is unique because there's only 4 cards of each kind. 2 people cannot have the same full house using the same 3 of a kind denomination. So it's easy to do the comparison. You don't care about the 2 of a kind. Okay. So 9s over jacks full house is higher than 8s over kings because you don't care about the jacks and the kings. You only look at the 3 of a kind. How many full houses are there? Well, this requires more tasks. From the 13 denominations, choose one of them for the 3 of a kind. But you still have some choices because there are 4 of those of the cards of that denomination. You need to choose 3 of them for the actual hand. Then, among the remaining 12 denominations, choose one for the 2 of a kind. Out of those 4 cards of that kind, choose 2. 3,744 different full houses. Next rank of poker hand is the flush. 5 cards of the same suit. And they are ranked by their highest card. A 10 high flush beats a 9 high flush. A 10 high spade flush and a 10 high heart flush, since the highest cards are the same, you look at the next ranking cards in each hand and work your way down to determine the higher ranking hand. If they're identical, you split the pot. Okay. How many flushes? Among the 4 suits, choose 1, like, for example, spades. Among the 13 spades, choose 5. 5,148. But you would want to subtract from this the 40 straight flushes, because no one would think of a straight flush as a mere flush. Okay, because flushes are a much lower rank than straight flushes. Next we come to straights. 5 cards of consecutive denominations. They are ranked by their highest card. So the number of straights is 10, choose 1. You choose the lowest card in the straight, for example. There are 10 possibilities. Choose 1. We did that for an earlier example. But now you've fixed the lowest card. There are 4 choices for that lowest card. The denominations of the other cards are fixed. If you've chosen a 5 for the lowest card, then you have to have a 6, 7, 8, 9. But there are 4 choices for each of those. So 4 to the 5th power, the multiplication rule. 10,240 straights. 3 of a kind. For example, this would be 3 sevens. Also ranked by the denomination of the 3 matching cards. Among the denominations, choose 1. Among the 4 cards of that denomination, choose 3 to put in your hand. Among the remaining 12 denominations, choose 2, because the rest of the hand has to consist of 2 cards of a different denomination. Otherwise, you'd have a full house. So choose 2 other denominations and choose 1 card of each denomination. 54,912 3-of-a-kind hands. 2 pair, like 5s and 3s. In this case, when you compare 2 pair hands, you first compare the higher ranking pair. If these are the same, you look at the lower ranking pair. If those are the same, you look at the 5th card. So here are some examples of the rankings. You know, the rankings are not important to counting the number of hands, but I thought you might want to know anyway. So for 2 pair hands of the 13 denominations, choose 2 of them. Then for each of those denominations, you have 4 cards, pick 2 from each. You have now you have to set aside 8 cards in determining the 5th card, because you don't want to end up with a full house. So there are 44 cards that are neither 5s nor 3s in this example here. Choose 1. 123,552 hands that are 2 pairs. 1 pair for each of the 13 denominations, choose 1. For those 4 cards, choose 2 for your pair. Now you need to choose 3 other denominations to make sure you don't end up with 2 pair or a full house. For each of those denominations, choose 1 card. 1,098,240. Now, if we take the sum of all of those counts, subtract it from the total number, 52, choose 5, we'll get the number of say, non-ranking hands. Now, they're still ranked by high card and second card and so on, but they don't have a name. There are 1,302,540 other hands. So now you know how to count poker hands. If this made sense to you, then you're catching on to the use of binomial coefficients in choosing things. If not, it might be worth going over this until all these make sense, because quite frankly, these are among the simplest problems in counting that there are. Now, as I mentioned earlier, to compute the probability of a given hand, you divide the number of hands of that type by the total number of poker hands. And that's what I've done here, and these are the probabilities. You can see that it's extremely unlikely to get a royal flush. Straight flushes don't happen very often either. They're quite rare. I can go for weeks playing poker, which I do semi-regularly, and not see a straight flush, not see four of a kind. Full houses, I see those modestly. If I play for 3 hours, I might very well see a straight flush. I mean, a full house, or two. Flushes are much more common, even though the numbers here aren't that much different. That's kind of interesting. Straights should occur a lot more than flushes. Okay, and three of a kind, that's still a pretty uncommon hand. Generally will win at Texas Hold'em. Not always, of course. Two pair, now we get, there's a huge jump here from two pair to one pair. This is almost 50%. So poker hands with a pair are quite common. It is 50% that you have nothing. Okay, so now you're ready to go play poker. But be careful. There's a lot more to poker than knowing how many there are of each type of hand. So I'm not advising you to play poker. Okay, thank you for watching this video, and I hope to see you in the next video.